Okay, so now we're in rational functions, and we just need to know how to plot them. And if you remember from an earlier section, the parent function f of x equals 1 over x looks something like this. So when x becomes large, f of x becomes small. When x approaches 0, 1 over x becomes very large, and then the same thing happens on the negative side. And it goes through the point 1, comma 1, because when x equals 1, y equals 1, and you go negative 1, negative 1. So that's the basic idea. There are, of course, more complex rational functions. A lot of times it's just a factor of knowing where the asymptotes are. Okay, so let's just start the homework. Problem number 18. So it says find any zeros of the rational function. So just like with polynomials, the zeros help us plot the functions. And in this case, we have h of x instead of g of x. Not that it makes any difference. So you get 2 plus 5 over x squared plus 2. So the zeros are also the x-intercepts. And the way you do that is the same way that you did with other functions. You just set y equal to 0 and solve for x. So there's a couple ways you could do that. You could first, if you have a rational function plus something else, the best thing to do in terms of finding the zeros is to combine these two with a common denominator. So I'm not going to set h of x equal to 0 yet. I'm just going to rewrite it. So what you do is you multiply and divide by the denominator of the second denominator in the rational part of it. Like that. And so now that you have a common denominator, and I don't know why I put 5. I guess because there's a 5 up there, but that's not correct. So it's plus 2, plus 2. Okay, so now we have a common denominator. So in the numerator, you've got 2x squared plus 2 times quantity times 2 plus 5, and you divide by x squared plus 2. And we can simplify it one additional step by combining the like terms that we have. So what you've got is x squared plus 9 divided by x squared plus 2. Okay. Now, if we now set the function equal to 0, the only way that can be 0 is if the numerator is 0. So the denominator really doesn't come into play in calculating zeros of rational functions. Now the problem here is that if you wanted to factor this, you can't factor it except for imaginary numbers. So if I put x squared on the left-hand side and put the 9 in the other side, it becomes negative 9. And so you get x is equal to plus or minus the square root of negative 9, which would be plus minus 3i. Those are not real zeros, so actually there are no zeros for this function. There are also no intercepts because the denominator So let's just go ahead and plot this function in the original form, 2 plus 5 over x squared plus 2. Two plus 5 divided by x squared plus 2. I think that's right. Yep. Okay, so we graph this thing. And what it looks like is that. So you see it it actually has vertical asymptotes, horizontal asymptotes of 2. It has a y-intercept of 4.5. But it has no x-intercepts or no zeros. You can see the y is equal to 0 when you set, the y-intercepts you set x equal to 0, so you'd get 0 here, so you get 5 halves plus 2, which would be 9 halves. That's how that happens. Okay, let's look at problem 20, which is another one. This one is already in the form, like that. Now, in this case, the numerator is greater than the denominator, but that really doesn't matter as far as the, it matters as far as the horizontal asymptotes, because when x becomes large, and the higher exponent in the numerator over compared to the exponent in the denominator makes so this thing goes to infinity. But as far as x-intercepts, it's not any different. So if you remember back to calculus, not calculus, because you haven't taken that yet, back to algebra 2, there are these special cubic functions, and if you had x cubed minus 1, it would be x minus 1 times x squared plus x plus 1, something like that. And the same applies here. So I'm going to put, I think one of the factors is x minus 2, if I remember correctly, and then there's a quadratic term. So this is the same as x equals 2 when I do synthetic division. So I'll put a 2 there. You bring down the 1. 2 times 1 is 2. Add those together, you get 2. 2 times 2 is 4. Add those together. 2 times 4 is 8. And you get 0. So what that leaves is x squared plus 2x plus 4. But that term is not factorable. You'll end up with it is factorable, but you'll end up with imaginary roots. So as far as the numerator is concerned, there's one value of x where the numerator goes to 0. So the 0 in this case, actually it's only one, the 0, not zeros. And actually it says find those zeros. So I don't know if it doesn't say real zeros, but I think that's what it's asking. And I'll double check here. So the zeros, we have 1 0, x equals 2, the only real 0. And that'll tell us where the function crosses the x-axis. But let me just pause for a second. So yes, that's correct. So that was the correct answer. There would be 2 other complex roots, but they're not zeros, because that means that that doesn't make the function go to 0. So I have to be careful about that. Okay, 21, the next group. So we got a large group of problems that have the same thing they're asking for. Identify all intercepts, find any vertical and horizontal asymptotes, check for symmetry, and plot additional points as needed, and sketch the graph of the rational function. So we'll do that, and then we'll plot it out using the graphing program. So the first one's pretty easy. It's just a translation of the parent function in the x direction. So if you think at it from a translation standpoint, you would say we would go -2, because you'll have x minus h, or whatever you want to call it, and so h is -2. So that would be -2 or 2 to the left. But let's answer all the questions they have. And intercepts, x-intercept. Well, that's where you set y equal to 0, and once it's in a single rational function, it's the values of x where the numerator goes to 0. Well, there are none, because the numerator is always 1, so it never goes to 0. The y-intercept, that's where you set x equal to 0 and see what y is. And if you did that, you get 1/2. So the y-intercept is a half. And that's those two things. Find any vertical or horizontal asymptote. So the vertical asymptote is where the denominator equals 0. So you set x plus 2, the denominator equal to 0. That gives you x equals -2. So that's the vertical asymptote. The horizontal asymptote is what happens when x becomes very large. And so we have 1 over x. So when x becomes very large, you have 1 over infinity, and that's 0. So y equals some number is the horizontal asymptote, whereas the vertical asymptote is x equals something. So you have y equals 0. Okay. And it says check for symmetry. So what do we see here? I always have a hard time with symmetry. There is symmetry. There's symmetry around the x-axis and about this line, vertical line, x equals -2. So anyway, we'll look at it. Let me put a piece of graph paper. And see what we can plot. Okay. So we have the y-intercept is a half. We're going to go from positive 10 to -10, positive 10 to -10. We have a vertical asymptote at x equals -2. We have a horizontal asymptote of 0. And we know we don't cross the x-axis because there are no real roots. So we know this one's going to go up like that. And another thing you think about is because it's just a simple 1 over x type function, you could go over 1, up 1. That would give you an additional point here. And you could go over 1, down 1. That would give you that point. So we can draw a pretty good sketch here. So this comes down through this point, through a half, then it'll approach the x-axis, and then you see the same behavior, and it is symmetric around the intersection of the vertical asymptote and the horizontal asymptote. So I don't think we need any extra ones to do that. And then we can go to the graphing program and just plot it. So it's 1 divided by x plus 2. Graph it. There it is. So you can see we have y-intercept of a half. We have this point which is 1 unit in the x direction. Notice the scales are a little skewed. 1 in the x direction, up 1. And then likewise you can go over 1, down 1 to get those points. And then you'd have the vertical and horizontal asymptotes. Okay, next is 24. So this is a similar one, except you got -1 over 3 minus x. So for the same reason, there are no x-intercepts because the denominator never goes to 0. The y-intercept is when you set x equal to 0, and you'll get 1/3. So y x equals 0, y equals 1/3. That's the y-intercept. You have a vertical asymptote at which has the equation x equals 3, because when x equals 3, you get 3 minus 3, which is 0. And the horizontal asymptote is the same as the previous problem, which is 0. I forgot to put the y here. And so it's y equals 0. Now what does this negative thing do? Well, you can kind of think of it as 1 over negative the quantity x minus 3. So what that's telling you is that the parent function should be shifted to the right 3 units. And the negative outside means that it is going to be reflected across the x-axis. So then instead of the initial function, the parent function looks like this. So what's going to happen is this thing is going to get flipped around like that. Okay, so let's see if we can use that information to sketch this thing. Okay, so we have no x-intercept, so we have a y-intercept 1/3, which is going to be right there. We have a vertical asymptote at 3. We have a horizontal asymptote of 0. And you can see that this point, the location of this point, shows you that this has to happen. Because what's going to happen is this thing's going to approach 0 as x becomes large from a negative sense. And then it's going to go through this point 1/3, and then it's going to go through this point 1, 1, because that's the parent function has that kind of behavior, and then it loops up, goes to the vertical asymptote. It'll come, you'll have a point right here again, and it's going to approach the horizontal asymptote from the bottom. It's going to go through here, and then it's going to go down. Has to go down for many reasons, because if it went up, you'd have an x-intercept, which we can't have. You also have, when you have a single 0, or a single horizontal, single result here, if it was x minus 3 times x minus 3, that would be double, but this is single. You always have the vertical asymptote go up one side and then zoop down to the other and come from the other direction. Okay, so let's plot this thing. 1 over 3 minus x. And do we graph it? There it is. So what we see here's this vertical line here would be the vertical asymptote. The horizontal asymptote, you see, goes to 0. If I go from this point of symmetry, I go over 1, up 1. Again, this is one whole unit, and actually we're going from here. Yeah, so that's x equals 3. So you go over 1 unit to 2, and then up 1 unit to 1, and you can do the same thing here. You go over 2, down 1. So those are the 2 points. This is the y-intercept. Just one a little bit. This says c of x, 5 plus 2x divided by 1 plus x. Okay, so this one's going to be different because there is a case where the numerator does go to 0. So the x-intercept, you set the numerator equal to 0. solve for x, you get x is negative 2/5. That's y equal, and y equals 0. So that's the point. The y-intercept, you set x equal to 0, which leaves 5 plus 0 over 1 plus 0, which is 5. So that's my y-intercept. So y-intercept would be the pair 0, 5. Up here, it would be negative 2/5, 0. You have your vertical asymptote. And that's where the value of x, where the denominator goes to 0, which in this case is x equals negative 1. And let me just continue on this so I can finish it. So then you have a horizontal asymptote. Now, because you have an x term in the numerator and the denominator, and now we have the same order. They're both the first power. So you take the ratio of leading coefficients, which would be 2 and 1. So the horizontal asymptote is a y equals something, and y equals 2 is the result. Okay, let's see what we can do here. So our x-intercept is negative 2/5, which is about right there. 0. Then you have 0, 5. So you go 1, 2, 3, 4, 5. That's my y-intercept. We have a vertical asymptote at negative 1. Like that. And we have a horizontal asymptote of 2, which would be, we'll just draw it out here. So I'm just thinking about how this thing might look. So let's go back and make sure it doesn't make any mistakes, because it doesn't look quite right. Well, the only way I could see this happening is that you can't come down on this side, because then you have an x-intercept, so it has to go along here and then kind of up like that, and then you cross the vertical asymptote, so you come up like this, you go through here, but then you'd have to loop back down so that you'd come to this point. So you go like that. And so I'm just thinking here, if there's anything we could use, we could look at 2 points. Let's look at x equals negative 3 and see what y is. So what we're going to do is we're going to do 2 points. So we're going to use x equals negative 3. So if we do that, we'll get y is equal to 5 plus 2 times negative 3 divided by 1 plus negative 3. So that becomes 5 plus 2 plus negative, so that's negative 1 divided by negative 2, which is a half. And that doesn't look right, because that would say it's down here. So, what am I doing wrong here? Oh, it's 5/2. That's what. It's not 2/5. It's 5/2. Again, yeah, I made a mistake, but that's okay. And it's going to be negative 5/2. Okay, so let's plot that. So that was the x-intercept. So we'll get rid of the old one. It just wasn't making sense. So sometimes you make mistakes. You have to go back and find your mistakes. Okay. So what we get is negative 5/2. So this is 1, 2/2, 4/2, 5/2. So that's my x-intercept. My y-intercept was 5. 1, 2, 3, 4, 5. This is making more sense now. And we did this point, which we said was negative 3 1/2. So that's there. So it's going to come along like this. It's going to go through there. It's going to come over and do that. And you should have a similar kind of thing here relative to this. If you wanted to use symmetry, if you think about this, we go 1, 2, 3. So we go over 1, up 3 from this kind of center point. So you go over 1, down 3. That would be the symmetrical point. And you could do the same thing here. Now, again, because there's a single root in the denominator, we know that if this goes down, then this has to come from the upward direction. So it comes down, it goes through this point, and then it's going to turn and come to this asymptote from that direction. So that one makes a whole lot more sense. I should have checked my answers earlier. Okay, so let's go back here. 5 plus 2x over 1 plus x. Now you have to, when you do this, you have to make sure you use the parentheses so that it includes the whole denominator and the whole numerator. Okay, so there we go. Let's zoom out a little bit in the y direction. So what you see is there's an x-intercept here at negative 5/2. You have this horizontal asymptote y equals 0. You have a y-intercept of 5. And if I were to draw the vertical asymptote and the horizontal asymptote, you'd see symmetry for this thing around this point right there, I think. Because you can see if I go over 1, I'll go down 1, 2, 3. And if I go over 1, I'll go up 1, 2, 3. So that looks correct. Okay, what's our next one? 25. The next one is 28. So what we have is f of x equals 2 minus 3 over x squared. We had one like this earlier, but it was something plus that. So again, what you want to do is, before you do anything, you need to find a common denominator. So the common denominator will be x squared. So we took the first term, multiplied by x squared over x squared. That'll give us a common denominator. And you combine those two together, and you'll get 2x cubed minus 2x squared minus 3 divided by x squared. Okay, so what do we got here? X-intercept. That'll happen when the numerator goes to 0. So if you solve that, you'll get 2x cubed, 2x squared is equal to 3, x squared is equal to 3/2, x is equal to plus or minus the square root of 3/2. And let's figure out what the decimal equivalent to that is. So 3/2 is 1/2, and take the square root of that, and you get plus or minus 1.22. Okay, so that's the x-intercept. The y-intercept is when you set x equal to 0. And what happens is that you've got something divided by 0, so there is no y-intercept because this would go to infinity, and that's because the vertical asymptote is at x equals 0, because that's the value of x where the denominator goes to 0. And notice it's doubled. It's a double root, so we're going to have something, instead of having something go like this, we're going to probably have something go like where they go in the same direction. Okay, what else can we do here? Horizontal asymptote. So that's where you look at the highest order term, which is x squared. They're equal to each other. X squared, they're both x squared. So you take the ratio of leading coefficients, and the result is the y value for the horizontal asymptote. So you get y equals 2. Okay, so we have two x-intercepts. We've got a horizontal asymptote. So let's plot what we know so far. Let's see if we can deduce what the heck's going on here. So we got an x-intercept, negative 1.22, which is about there. Another x-intercept, positive 1.22. There's no y-intercept. And there is a horizontal asymptote at y equals 2. And there's a vertical asymptote at x equals 0. So what's going to happen is the function is going to come along here through the horizontal asymptote. It's going to get close to here, and it's going to go negative, and then it's going to have to keep going negative because there's no other x-intercept, and there's a vertical asymptote here at 0. And the other side has to do the same thing. It's going to have to come in from the bottom. It's going to have to go through here and then head south like that. And that's because of this fact you have x squared in the denominator, because you got x equals 0 and x equals 0 twice. When you have two of those, you get this behavior where instead of going opposite directions of the vertical asymptote, they go the same direction. Okay, so let's plot that thing out, and we'll do it with the beginning formula. So it's 2 minus 3 over x squared. So what we have is we have 2 minus 3 divided by x squared. There it is. Here's our negative x-intercept. Here's our positive x-intercept. Here's the horizontal asymptote. You see they're approaching. Y equals 2. The vertical asymptote here is 0, so these both go down in the same direction. They keep going. If I zoomed out in the y direction, you can see that they approach the asymptote. Okay, I think we're not quite finished. We've got one more in this section. 37. So we have is 3x divided by x squared minus x minus 2. So if we could factor the denominator, that would be nice, which we can. So we get x here, and what two numbers multiplied together give us -2? Well, -1 or +2 or the other way around. So I'm just going to put 1 and 2 right here. And look at the middle term. The middle term is negative, so that means that the negative has to go with that one and the positive has to go with that one, so that you get a net negative from the outer and inner. So x-intercept, that's when the denominator equals 0. So that occurs when x equals 0. So we have an x-intercept at 0. Our y-intercept is when we set y equal to 0. We set x equal to 0. So if we set x equal to 0, we'll get 0. We get y equals 0. So in this case, the x-intercept is 0, 0, and the y-intercept is 0, 0. So we know it goes through the origin. We have two vertical asymptotes. That's where the denominator equals 0. So since we have it factored, it's easy to see it's going to be when x equals 2 and when x equals -1. So those are the actual equations for the vertical asymptote. And then we have a horizontal asymptote. And that's just going to be y equals 0, because we have this, the highest order term in the numerator is x to the first power. The highest order term in the denominator is x squared. So since this is less than that, the asymptote is y equals 0. Okay. So let's add a page. Add my graph paper. So let's plot what we got here. Okay, so our x and y intercepts are right here. We have a vertical asymptote at x equals 2 and x equals -1. We have horizontal asymptotes of 0. So what's going to happen here is you're going to come along the x-axis, then you're going to go up this way, and because there's a single root here, it's going to come from the other side, and then it's going to go up through here and then approach this vertical asymptote, and then it'll flip over, come from this side, and then it'll go up and then go around like that. Now just to prove that that's true, let's just do 2 additional points. So let's do x equals -2, and so let's do that first. So what I'm going to do is add a page here. So if you do x equals -2, f of -2 is going to be 3 times -2 divided by -2 squared minus -2 minus 2. So the numerator is -6. And at the denominator we have this +4, +2, so that's +6. +6 minus 2 is +4. And so we get -3/2 if you simplify that down. So that's f of -2. So let's plot that. So it's -2, -3/2. So we got -2, -3/2, which is that point. So that makes, so we have to be in this little quadrant. And if we go 1, 2, 3, let's see, 1, 2, 3. So what we're going to do is we're going to do x of 3. That's going to be on this side of the vertical asymptote. Okay, so what we want is f of 3. So that'll be 3 times 3 divided by 3 squared minus 3 minus 2. So this is x squared minus x. So you get 9 divided by, so you have 9 minus 3 minus 2, that's going to be negative 4, it's just going to be 4. 9 minus 5 is 4. So you get 9/4. So if we go over 1, 2, 3, 9/4 is going to be about, that's 8/4, 9/4 is going to be about there, which again places in this quadrant. So now it does go along with what I said. So it comes down here, goes through this point, and loop around, approach the x. Now because this goes up and there's only a single root there, it's going to come from the opposite direction. So it'll come up here, and then okay, we never plotted, well, we didn't need to plot the y-intercept because that is there. So it goes right through there and then bends around and heads on up this vertical asymptote. And again, because there was a single value here, it pops down on the bottom, comes from negative infinity, comes up here, and then bends through that, and then approaches the horizontal asymptote from the bottom. And that's it. Okay, so let's plot that. And let me look at my book so I get this right. Okay, so the function was 3x divided by x squared minus x minus 2, right parenthesis, graph it, and there it is. So you see we have vertical asymptotes at -1 and +2. We have our x and y intercepts here, and otherwise you can, if we bounce back, you can see that slightly different scale, but I guess if I did the same scale, how do I do the scale here? Oh, okay. So if I went from -10 to +10 and from -10 to +10 and I graphed it, it looks like that, which is closer to what mine looks like on the next page. Again, it's kind of squished up in one direction. Okay. Now we're moving on to another section of problems. Oh no, actually we still got one more. So this is the most difficult one that we have to deal with. So we've got x squared minus x minus 2, which we already know how to factor because it was the last problem. And then the denominator we have x cubed minus 2x squared minus 5x plus 6. So the numerator is easy. It's going to be x minus 2, x plus 1. Like I said, we just did that in the previous problem. Now the question is, what are the intercepts here? And my guess is that it's not going to be 2 or -1, because then they would cancel out. So I'm guessing that x equals -2 might work, or x equals +1 might work to find the asymptote. So let's just try x equals 1, see what happens. So we're gonna divide this by the 0 that we think this would result when you factored it. So you got 1 minus 2 minus 5 plus 6. So you bring the 1 down. 1 times 1 is 1. -2 plus 1 is -1. -1 times -1 is -1. Add those together, you get -6. -6 times 1 is -6. You add those together, you get 0. So that was one of them. And what we're left with is x squared minus x minus 6. And that one we can factor by just by observation. Two numbers multiplied together give you 6, whose difference is 1. The answer would be 3 and 2. So you get 3 and 2, and because the x here is negative, you put the negative on the bigger one and that. So this other one that I thought might be it was also it. So you basically have the denominator could be factored as x plus 2. That would be the factor associated with this. There it is anyway, I have down there, x minus 3 and x minus 1. That would be the factor associated with that, 0. You see nothing cancels out. And so the x-intercepts, that's when the denominator equals 0, which since it's already factored, that's easy. That's going to be when x equals 2 and when x equals negative 1. So the x-intercepts are going to be 2, 0 and negative 1, 0. Those are the coordinates. Okay, the y-intercept, you only have one y-intercept with functions. You would set x equal to 0, and you would get y is equal to negative 2, 6 from the constants. That's negative 1/3. So that's my y-intercept. So I'd have 0, negative 1/3 would be the point. Then you have the vertical asymptotes, and that's where the denominator goes to 0. So there are 3 cases. X equals negative 2, x equals positive 3, x equals 1. So those are my 3 vertical asymptotes. And my horizontal asymptote is going to be y equals 0, because if I go back to the original form, you see I've got x squared in the numerator and x cubed in the denominator. Because that's smaller than that, that gives you that's the result. So let's put all that into a graph and see what we got. Okay, not sure why it's letting me not drag that. Okay, there we go. Let's plot the intercepts. So you've got 2 and negative 1. 2 and negative 1. Did I get that right? 2, negative 1. Okay. The y-intercept is 0, negative 1/3, which would be about right there. Let's draw some vertical asymptotes. So we have one at negative 2. We have one at positive 1. And we have one at positive 3. And we've got a horizontal asymptote of 0. So there's a couple of ways you could do that. We could put in x equals 1, 2, 3, 4 and find out whether it's up here or down there. And you could do the same thing. You could go negative 3 and see which way you're going. But there's actually another way of doing this. You could start kind of here in the middle. So this one's lower than that one. So it has to pass through like that. And it has to go down this way, because if it went up, there would be another x-intercept there, which there's not. So that's got to go down. It has to come through here. Then it's going to go through there. It has to keep going up, because if it went down again, then it would cross the x-axis and we'd have another x-intercept. Okay. Now on this side, because this one is going up, this one has to come from the down direction. So it would come on this vertical asymptote, and then it would kind of cross over, and then it would have to approach the vertical asymptote here from the bottom. Can't cross the x-axis because there are no x-intercepts. Okay, so now we go the other direction. Because it was going down, this side of the vertical asymptote has to be coming from the other direction. So it comes down from positive infinity. then crosses the x-axis here like that, and then it has to keep going down because there's no other x-intercept. So the only way to keep going is to keep going down to negative infinity. And again, crossing this this vertical asymptote means it has to come up here. It's going to come down, and then it's going to curve, and it's going to bend towards the horizontal asymptote. And again, it can't cross the line because there are no x-intercepts from here outward. So let's just prove that this is true. What did I say? So this is the origin, 1, 3, 4. So if I go to, let's go to 5. So if we plug x equals 5 into the original equation, so I'm going to do x equals 5 here, you'll get 5 squared minus 5 minus 2 divided by 5 cubed minus 2 times 5 squared minus 5 times 5 plus 6. So in the numerator you've got 25 minus 5, which is 20, minus 2, which is 18. So that's 18. And then the denominator we have 5 cubed, which is 125, minus 2 times 5 squared. 5 squared is 25, so that's 50, minus 25, minus plus 6. So we get, so that's 75, 50, 56. And is that, what is 56 divided by 18? It doesn't quite simplify down, but it's, so if we simplify it, let's just divide by 2, you'll get 9 divided by 28, and I guess that's it. Can't go any further, so I just divide them both by 2, and then you can only divide 9 by 3, and you can't divide 28 by 3, so you get 9 28ths. If you try that, compare it with 18 divided by 56, you'll get the same number. So that's like 0.3 something, 32. So if we go over here, oops, that's not where I wanted to go. So if I go, so I have 5 comma 0.32. So I'll go 1, 2, 3, 4, 5.32 actually. So we really come down a little bit tighter than that. Probably the same thing's going to happen over here. It's going to pretty tight curve. Okay. Okay, so that was 40. '51. Identify all intercepts, find any vertical slant asymptote, check for symmetry, and plot additional points. So these are slant asymptote situations. So, and that's because the numerator is a higher order than the denominator. So we can find the x-intercepts by leaving it in this form. And so what you do is you'd set the numerator equal to 0. And so you get negative 2 equals 2x squared. And then you're like, I can't do that because I can't take the square root of a negative number. So there are no x-intercepts. Y-intercepts, the problem there is that when you set x equal to 0, you're going to divide by 0, which is undefined. So that doesn't work either. So there are no y-intercepts. Then you have vertical asymptotes. So that is when the denominator goes to 0. So when does x equal 0 equal 0? Well, it's when x equals 0. So the vertical asymptote is a line x equals 0. And the next part is the slant asymptote, because you don't have a horizontal asymptote because the numerator order is greater than the denominator. So what you do is you just use long division and rewrite this. So you're going to have 2x squared plus 0x plus 1 divided by x. So how many times do I have to multiply x by to get 2x squared? Well, the answer would be 2x. So you take 2x times x, you get 2x squared. We're subtracting that, so that goes to 0. Then you bring down 0x, and how many times do you multiply x by to get 0x? Well, the answer is 0. And so then you just bring that down. So what you end up with, the original expression can be written as 2x plus the remainder, 1, divided by the original denominator. So the slant asymptote is the non-remainder part, just the part that's at the front, and it's y equals that. So you'd have y equals 2x is the slant asymptote. Okay, so let's see what the thing looks like. So we don't have any x or y intercepts, but we do have a slant asymptote, and that is going to be y equals 2x. So that's going to look like this. It's going to go over 2, over 1 up 2, over 1 up 2, over 1 up 2, and I don't quite have it right yet. So when it goes over 5, it should go up 10. So that'll work. There we go. That works out. And then I just pull this all the way down to, so I go over, there we go. And everything, over 1 up 2, over 1 up 2, over 1 up 2 up 2. So that's the slant. Now we have a vertical asymptote at x equals 0. So that's the vertical asymptote. So if we were over here, that wouldn't work out because you'd have a slant asymptote, but we don't have a horizontal asymptote. So we know this has to be contained in this little v, and this other part has to be contained in this little v. And probably the best thing to do is to find one extra point. So we're going to find it at 1, and because of symmetry, it's going to be the same distance down. So what we'll do is we'll go back to the original function, and we'll evaluate it at x equals 1. So f of 1 is 2 times 1 squared plus 1 over 1. So that's 3 over 1. You get 1 squared is 1. 1 times 2 is 1. 2. 2 plus 1 is 3. Okay, so we have the point 1 comma 3, and as for symmetry, we'll have negative 1 comma negative 3. So 1, 1, 2, 3, so that's a point, and 1, negative 3, that's another point. So this thing's going to come down from here. It's going to go through this point. Exactly where it happens, I'm not exactly sure. You'll take calculus to know where the minimum is, but that's the general idea. And then you have the same thing happen. So this is, as x approaches negative infinity, it approaches the slant asymptote, then it'll come in here, it'll turn around, and then it'll go the opposite direction. Now I can't keep going straight because then you'd have an x-intercept. Okay, so that's the function. Let's plot it out. 2x squared plus 1 over x. That's all right. So 2x divided by x. Actually, x squared plus 1 divided by x. Graph it. Here you go. If we plot the line y equals 2x, so just put 2x in there, you'll get that. And so, and you can also see if I go over -1, 3 and +1, 3, it's not quite the minimum, but it's pretty close to it. So that one's good. And one last one, which is 53. So we have g of x equals x squared plus 1 over x. That one actually looks too much like the last one, so I'm going to do 54 just to do something different. So you got h of x equals x squared over x minus 1. So here we have the x-intercept is going to be where the numerator is equal to 0. So that happens when x equals 0. The y-intercept is when you set x equal to 0. So it's the y value. So you get 0 squared over 0 minus 1, which is 0. Because you get 0 over -1, which is 0. So the x-intercept is going to be 0, 0, and the y-intercept is the same thing, 0, 0. Okay. Now, we have a vertical asymptote. That is going to be where the denominator equals 0, which is x equals 1. And then we calculate our slant asymptote, so we're going to take x squared plus 0x plus 0 divided by x minus 1. What do I need to multiply x by to get x squared? X. X times x is x squared. X times -1 is -x. We're subtracting that, so those cancel out. Here you have 0x plus x. So you get x, and then you have plus 0. Bring this down. What do I need to multiply x by to get x? The answer is 1. 1 times x is x. 1 times -1 is -1. We're subtracting those, so those cancel out. You get 0 plus 1, which is 1. So this original expression could be written as x plus 1 plus 1 over x minus 1. So the slant asymptote is y equals x plus 1. It's this part. Because when x gets large, this goes to 0. So now we're going to plot what we can plot and see if we have enough to make a reasonable graph. Okay, so the slant is this. So that is it intersects the y-axis at 1, and it has a slope of 1. So it's going to go like this all the way up to there, and then it will continue on in the other direction. So there we go. Okay, so that's my slant. My vertical asymptote is at 1. So that's going to be here. Oops. So my vertical asymptote is going to look like that. And based on the last one, it should look something like this and like that. Notice that the x and y intercepts are 0. So I know it's going to go through this point. So it's probably going to go something like this. It's going to come up here, and then it's going to loop around. And it's going to back down here. And likewise, there's probably a point of symmetry here. So it's down 2 over 1. So if I go up 2 over 1, that looks like about, that would be the symmetric point for this thing. You get that. So let's graph it. So the function was x squared divided by x minus 1. And I'm going to plot the slant asymptote, which was x plus 1. And there we go. Notice it goes through 0, 0. Here's the symmetric point. Again, it looks a little different because of the scale that we're using. You know, I'm squishing things up in the x direction, but you know, the intersection of the vertical asymptote and the slant asymptote is right here. So everything's symmetric about